You finally finished throwing stuff at me? Finally finished with all these drawings? He's been drawing stuff over here for, I don't know, seems like an hour. I guess that's not long when you're 400 and something million years old. But let's look at all these pictures that Yuri got for us. So, first one. What is that, Yuri? So, let's see if we can decipher Yuri's drawings here. This looks like an, does that say epicenter? Yeah, epicenter. So this is obviously a drawing of the inside of the Earth. That would be where, like I say, an earthquake happened, and you've got all those P and S waves going through the entire Earth. So, some things to remember. The P waves can go through everything, and the S waves, they can't. So one of the ways that we figured out what's going on inside the Earth, what's liquid, what's solid, is by analyzing the seismic data. Hopefully I did something like fancy over here. That's a really common question. Analyzing seismic data is how we know what's going on inside of here. So we look at that earthquake data. The P waves, they go through everything, and they go through first, they're primary, and then the secondary waves are a little slower, but they can't get through the liquid. So that's how we figured out that this outer core is liquid, and then this inner core is solid again. So using seismic waves, we'll go over in more detail with the reference table series of videos on how to answer some more of those questions, but that's the basics of what's going on inside the Earth. Okay, and then one other thing to remember, Yuri could have drawn on here, I'll draw it quickly. So we're going to kind of zoom in on, let's circle in this color here. If we zoom in on this little box right there, we're just going to look at the crust, and just underneath the crust, the asthenosphere. Okay, that's the plastic mantle. That's where all the good stuff happens. Yuri just can't stay still today. Guess he doesn't like my Syracuse shirt. So we're going to be talking about arrows that do this. Okay, those arrows were heat rises. Warm rock, less dense rock rises up, and then the cooler rock sinks back down into the Earth. That's convection. So convection is like the most important thing with, that's what drives plate tectonics. So if we look at the different types of tectonic plate boundaries, okay, you got to remember the evidence for plate tectonics, right? We'll go through some questions with that. The continents look like they fit together. Okay, you have fossils match up. That's called correlate. When they match up across continents, the rocks and the minerals also match up across the continents. And then we'll look at how when the rocks separate in this one right here, nice drawing, Yuri. Okay, this type of boundary here, when the rocks separate, this is underneath the ocean. So if we're looking at this right here, maybe it would have been helpful, Yuri, if you drew the ocean surface there. So ocean. That's the ocean, and these are the crustal plates underneath the oceans. Okay, so as these are pulling apart, it's called a divergent boundary. Okay, the convection happens in the plastic mantle. It's not liquid, it's gooey. It's really close to being melted, kind of like ice cream. You know, when it's the cat's pajamas, when it's just like super close to melted, but not quite close, but it can flow, but it's not solid. That's the cat's pajamas. So just kind of like that consistency. Heat rises, convection's happening, and it's pulling apart those crustal plates. Okay, and that's another piece of evidence. There was this, I'm not going to try to add to Yuri's artwork here. There was a ship that this guy, Harry Hess, was taking these readings of the crustal rocks, and as he got further away from where the volcanoes happen here, he noticed that there was this magnetic pattern that kept flip-flopping, and it was identical on the other side of the crust. And so that matching up the magnetic polarities from switching North Pole, South Pole, as the magnetic signature of Earth is flip-flopped over time, you can see that in the rocks. Okay, we also notice that these rocks over here are old and cold, and these rocks right here are young and hot. So if this rock here is a certain age, it exactly matches up the rocks over here in age. Okay, we'll do a few questions on that. Divergent boundaries. Another great drawing from Yuri. Good artwork here, pal. I don't know if this makes sense or not, but you've got some CC. You've got continental crust, okay, and the the convection currents are driving plates together at some points. Ocean crust, this is called subduction. The ocean crust is sinking. And right here, let's draw the ocean in. Put that in purple since I'm holding that up right now. It's really not a good drawing, but sorry, Yuri. Okay, I should have drew the ocean lower than the level of the continent here, but you've got the ocean. Underneath the ocean crust here, this is called a trench. These are some of the deepest parts on Earth. And as this ocean crust sinks, subducts back into the Earth, it melts, partial melts. Lava comes up, well, it's magma at this point, but the magma's rising, turns into lava, and you get these volcanic chains there. So this can happen with all the different types of crust. Ocean and ocean crust, when they collide, one of them will sink and you'll get an island arc. Okay, and that's like Japan when you have that thin chain of islands. You okay, Yuri? We'll get him in a second. He's just crawling around down there. You can have two continents collide, and when those two continents collide, neither one of them is really more dense, so neither one of them wants to sink into the earth, and that's when you get the biggest mountain chains, like the Himalayan mountains. And then the one that I just drew, the more dense crust, which is the ocean crust, it's made of basalt, that'll sink, and you get that ridge of mountains and volcanoes, like the Andes Mountains in South America. Sorry, Yuri, your exoskeleton okay? All right, and then that's a good drawing, Yuri. I'm proud of you. Not the best drawing in the world, but what you've got is transform boundary. So some plates, they're just sliding by each other. So rather than colliding or pulling apart, they're just kind of like moving past each other. You don't get much volcanic activity with these, but you do get a lot of earthquakes. California, San Andreas Fault is probably the most commonly known one. And you'll actually see some displacement. So if this plate is moving this way and this plate is moving this way and a river flows out, you even included an oxbow lake. There's a blast from the past. Review video number, I don't remember. Oxbow Lake. So that's an old river feature. You've got some meanders. But when the river flows across the crustal boundary, the plate boundary, you can see some displacement. Or that's probably railroad tracks that Yuri drew. So you can see displacement. Things will actually move. We're only talking centimeters per year, but over time you will see some displacement on those things. So I think that's all the drawings that Yuri did for us. We'll go back over all the same stuff with some of these questions, and I'll see you back here after our practice questions. All right, so this drawing might be a little bit better than Yuri's drawing, but that's okay. Now, we did forget to mention the shadow zones. So because when waves are going through different density, materials with different density, they'll actually turn, they'll refract, they get bent. And because it's going through some liquid right here, the P waves get bent a little bit and you find no seismic waves on either side of the Earth. So those are shadow zones. That's another piece of evidence that basically it all comes back to how do we know what's going on inside the Earth? We look at the seismic data. So for this question here, which one would you want to pick? If I'm reading through here, P waves are refracted and S waves are absorbed by that liquid outer core. That was a tough question. It took me, I wasn't stalling. That's how long it took me to read and make sure that that was the answer that I wanted. So P waves go through everything. S waves can't go through liquids. All right, 2 questions for 1, just because it takes so time to copy and paste all of these things in here. I think we forgot to mention, and by we, I mean, it's all me, it's not Yuri's fault. Continental crust is thicker. So that's, I mean, it's pretty obvious in all the pictures that you see, but continents are thicker, ocean crust is thinner, and that's why the water builds up there. So when you're comparing A to B, compared to the crust at A, the crust at B is. This is a good time just to bring up, New York State Regents loves to kind of what I call like bait and switch, or they do like a head fake. They start talking about one thing. Here they're talking about the crust at A, but then they flip-flop and they say the crust at B is. And I know my brain wants to, I'm thinking A, so I start to try to describe A. But I'm really describing B here, and that's really important to keep an eye out for that. It's a really common thing that they do. So crust at B is, that's ocean crust. It's going to be thinner and more dense. So I would go with choice B. Geologists have used information about the composition of meteorites. Also forgot to mention that one. So when the Earth formed, it was a collision of many small meteorites and minor planet that came together to grow into the Earth. And we look at the composition of the meteorites, and it is similar composition to the Earth's core. When those meteorites hit, the most dense heavy metals sank to the center, like the irons and the nickels. All right, we'll look at a couple more questions here. I see some different places on Earth labeled, different types of crust, different features. Which one's going to be the youngest? So let's look down here. These crusts, these are different questions, but you could always use questions on a test to help you with other questions on a test. So the crust is pulling apart there. I'm going to switch right because I need to show some magma. All of this is magma. Remember that. This is a huge volcanic island or volcanic mountain chain underneath the ocean anytime you see a ridge. And so when these plates are pulling apart here, you've got the magma here. This is going to be the youngest and the hottest. And then out here is the oldest and the coldest rock. So the youngest rock there would be C. Okay, and then sometimes they'll have you match up. How far away is X from the divergent boundary? So I'm going to need some sort of way to measure. I'm going to draw a line to measure. Okay, so if this is my distance there, if I could take that line and look over here, which one best matches up? Wow, I really, looks like I drew my line just a hair too big. So if I shrink it, this is probably easier to do on paper. If I shrink that line and then bring it over here and try to turn the line, it looks like probably 8 is the closest. Yeah, very tough to do on my screen here, but you would measure with a piece of paper, make 2 marks and slide that over. So it looks like 8 would be the closest. But basically the concept is however far away you are here, that same distance over here is a match. This goes back to that magnetic striping or magnetic reversals, the polarity reversals. So this is an exact opposite pattern. You see the mid-ocean ridge here. As you go away, this is the young hot rock. The older and colder rocks, you can see North Pole and South Pole flipping. It's going to be the exact opposite over here, a mirror image. So which of these 4 is a mirror image? I've got a big gray, small white, and then a medium-sized gray, big, small, medium. It looks like choice A would be my choice there. This one does a nice job of showing the convection currents, and only 2 of them are possible options right off the bat. If I get my pen here, right off the bat, I cannot use the pen here. Won't work now. Right here. No, those 2 don't make too much sense. We don't really see that. You're always seeing convection currents. So which one is showing the pulling apart of a ridge? And so we've got pulling apart right there. So that looks like the divergent boundary there. This would actually be, if we completed that cycle coming back together here, that would be a convergent boundary at A. So this is looking like a divergent boundary here. All right, so if we look here, some evidence for plate tectonics. We have 2 places that look like they kind of match up across here. And so basically the fossils match up, the rocks match up, the minerals match up. It's called correlation. And so which answer here best explains why the 2 fossils show up on both sides? Looks like choice C. All right, so on this one, I liked this a lot because it shows that tectonic plate boundary, and it also shows what an island arc would look like. So when North America was forming, okay, you've got the North American plate here colliding with another plate that basically became part of the North American plate now. But you can see like there's a little bit of ocean here, and this was ocean crust to begin with, pretty much. And so as that ocean crust is colliding with more ocean crust, this is where you get this island arc peaking up. And then as it kept colliding and colliding, you started to make like Mount McKinley, and you get that collision happening right there. So the type of plate boundary represented in the cross section, they give you a ton of stuff to basically ask a very simple question. Okay. Now I am easily distracted by these things because they're so cool to look at, but basically what you're looking at is this arrow here and this arrow here, they're colliding. So that's a convergent boundary. So this is another convergent boundary. So my answer would be B. It basically shows that picture we drew earlier. You've got the thin ocean crust, the thick continental crust. You get some melting. A lot of times they'll actually have you draw the arrows in part C on the short answer part of the test. And when they want you to draw the arrows, just make sure you're very clearly showing either colliding or pulling apart. I just basically picked these more to show you a few of the diagrams. Here you have a convergent. This is continental to continental collision. Here you have a divergent with the ocean crust ripping apart. Okay, that's called a ridge. You have the ocean and continent colliding. This is when you get that trench right there. This would be like the west coast of South America. That's another convergent. And then this is that transform boundary. Okay, and then you can see here with the subduction zone, so you get that subduction, that means going into the earth. The further you get from the plate boundary, the deeper the earthquakes will get. So remember, that's called a focus, and then the epicenter is the point directly above the focus. And then this is just a really cool picture. It's a very much more detailed picture than you usually see, which is kind of why I pointed it out, and I can see why this would be a really confusing thing for somebody to come across on a test. What they're showing here is this is basically pulling apart and pulling apart. You can see how the they call it the Rift Valley. Okay, the Rift Valley, you can see that the crust just gets thinner as it's getting pulled apart. It's kind of like when you pull silly putty apart, or taffy, or an airhead or something like that. As you pull it apart, it gets thinner and thinner until it breaks. So this is a rift. That's a divergent boundary. They did put the word rift up here to make it easier. You didn't have to just go off of this really kind of technical diagram. So just don't forget to read those things up there. And that's all the questions I had for you. Back to Yuri. All right, so those were the review questions. Yuri, you got one more note for me? What's this say? Not so hot. What's that supposed to mean? Oh, I forgot hotspots. So we'll go to a quick animation just to explain how hotspots like Hawaii formed and what happens there. And that's all I got. All right, so let's watch this little hotspot animation here. You can see the magma builds up. That's just my dog Mud. And as that plume, that's called a plume of magma just coming up. Now this continental plate is moving over that plume. So over time, as the plate moves on, this is a dormant volcano, and you can see it shrinking because of all that wave action, okay? And there's just a long line of volcanoes that build up. And as that long line of volcanoes builds up, you start to get this chain of volcanoes. And this is what Hawaii, this is how Hawaii actually formed. So this is why none of these other islands of Hawaii have active volcanoes. Only the current island is getting bigger and has lava flows. But over time, they keep moving, and eventually they get worn down underneath the surface of the ocean by all that wave erosion. So the further away you get from the hot spot, the older and older and older the rocks are. Almost forgot that part.